Today let's talk about function. The concept of function is one you have seen many times already, so it is hardly necessary to remind you how central it is to all mathematics. A function is usually thought of as a rule that assigns to each element of a set A an element of a set B. Here comes the informal definition of a function. Let AB be sets. F is a function from A to B exactly when F is a rule of assignment from A to B, so that each element of x of A is being assigned to exactly one element, namely f of x of B. A is called the domain of F. B is called the codomain of F. The problem of the above informal definition is that it is not clear what we mean by the phrase rule of assignment, which is crucial in explaining the mathematical meaning of the word function. To solve this problem, we try to formulate an appropriate definition for the notion of function in terms of something that we understand better mathematically, which are right in terms of the language of sets. But what kind of sets shall we be looking at? In order to understand what a particular function does, we study its graph, which is a subset of the Cartesian product of the domain and codomain. In fact, the graph of the function contains exactly all the information about that function. We can recover from its graph what the function does as a rule of assignment from its domain to its codomain. Hence, we focus on how to make sense of a graph of a function in terms of the language of sets, instead of making sense of rule of assignment. Here comes the formal definition of a function. Let AB be sets, and G be a subset of A times B. The order triple ABG is said to be a function from A to B if both of the statements EU below hold. For any x in A, there exists y in B such that x, y belongs to G. U. For any x in A, for any y, z in B, if xy belongs to G and xz belongs to G, then y is equal to z. ABG are respectively called the domain, codomain, and graph of this function. When we refer to ABG as f, we write y equals f of x exactly when xy belongs to G. Declaration. We can define a function by making a declaration. When we define a function, say f from A to B, in very simple situations, we often write in this way. Define the function f from A to B by fx equals to so and so. For example, define the function f from R to R by f of x equals to x squared for any x belonging to R. Given functions f from A to B and g from B to C, we define the composite g compose f of f and g as the function g compose f from A to C defined by the equation like this. Note that g compose f is defined only when the codomain of f is a subset of the domain of G. The idea is illustrated in this diagram. You pick a point A in set A, then you have f to map it to f of A, which is in B. And then you map the element f of A by G to the set C, and the element is G of f of A, which is equal to C. Now, we introduce the concept of injectivity, surjectivity, and bijectivity. Let AB be sets, and f from A to B be a function. F is said to be injective if for any x, w in A, if fx equals fw, then x is equal to w. In other words, when you put different inputs into the function machine, the machine will give you different outputs. F is said to be surjective if for any y in B, there exists x in A such that y equals fx. F is said to be bijective if f is both injective and surjective. Inverse function. Let AB be sets, and let f from A to B, g from B to A be functions. G is said to be an inverse function of f if both of the following statements hold. Statement 1. For any x in A, G compose f x is equal to x. Statement 2. For any y in B, f compose G of y is equal to y. Uniqueness of inverse function. Theorem 1. Let AB be set, and let f from A to B be a function. F has at most one inverse function. Here comes the proof. Suppose G, H from B to A are both inverse functions of f. We want to show that G of y is equal to H of y for any y belonging to B. If we can show this condition, then means G and H are the same function. Let y belongs to B. Define x equal to G of y. Then x belongs to A. Then y equals to f of G of y equals to f of x. So h of y is equal to h of f of x equals to x, which is G of y. It follows that G and H are the same function. Necessary condition for existence of inverse function. Theorem 2. Let AB be set. F from A to B be a function. Suppose f has an inverse function, say G from B to A, then each of fg is bijective. Proof. Let x, w belongs to A. Suppose f of x is equal to f of w, then g of f of x is equal to g of f of w, then x equals to w. So f is injective. Let uv belongs to B. Suppose g of u is equal to g of v, then f of g of u is equal to f of g of v, then u is equal to v. So g is injective. So we have to show f and g are surjective, and we will do that in the next page. Let B belongs to the set B. Define A equals G of B. We have A belongs to A. Note that f of A equals f of G of B equals B. So there exists A in A such that B equals f of A. Therefore, f is surjective. Let C belongs to A. We define D equals f of C. We have D belongs to B. Note that G of D equals G of f of C equals C. So there exists D belongs to B such that C is equal to G of D. Therefore, G is surjective. Therefore, both f and g are bijective. Bijectivity is a necessary condition for existence of an inverse function. It is natural to ask, is the necessary condition sufficient? The answer is yes. Existence and uniqueness of inverse function for a bijective function. Theorem 3. Let A, B be set, and f from A to B be a function. Suppose f is bijective. Then there exists some unique bijective function g from B to A such that g is the inverse function of f. Let f be a graph of f. Define G to be the set containing all y, x such that x belongs to A and y belongs to B and x, y belongs to f. Then G is a subset of B times A. Define G equal to BAG. First of all, we have to show that the ordered triple G, this one, is a function. As f is surjective for all y in B, there exists x in A such as x, y is in f. Then y, x belongs to G. As f is injective for all y in B, for all x, w in A, if x, y belongs to f and w, y belongs to f, then x is equal to w. Then if y, x belongs to G and y, w belongs to G, then x is equal to w. So G is a function from B to A. Pick any x belongs to A, y belongs to B. Y equals fx if and only if x, y belongs to f, if and only if y, x belongs to G, if and only if x is equal to G of y. Let s belongs to A. Define u equals to f of s. Then u belongs to B and s is equal to g of u. Then g compose f of s equals g of u equals s. Let v belongs to B. Define t equals to g of v. Then t belongs to A and v equals f of t. Then f compose g, v is equal to f of t is equal to v, it follows that g is the inverse function of f. Then g is bijective by theorem 2. Also, g is unique by theorem 1. So the proof is complete. This is the end of the presentation. If you find my video interesting, please consider subscribing my channel, liking my video, and commenting down below. Thank you. See you in the next video.